on. Okay. Hey, everyone. Good morning. You know now. You're good. Good morning. It's great to see you again. When you make it sound fake like that, Mike, it doesn't work. All right. Yeah, I love it. Okay. So the past 2 days, we have done a somewhat large amount of math together. And I wanted to spend today emphasizing some potential, go through some ideas. And this will be a little bit less work on pen and paper on the quote unquote board. And then I'm going to switch over to some slides with some data and things like that. It's a screen competition, so my data is mostly simulation data, sorry. But nevertheless, not as beautiful as like Mike's stuff, but that's okay. So last time we wrote down and discussed at some length the equation for vertex models that showed up in the literature. In particular, I used the version that showed up in the Hardy-Farr paper from 2007. Okay, and I wanted to start there today, and I wanted to say, okay, you that has a lot of different cells, and those cells could potentially have different properties. You know, you had a rest length for, you had a surface tension associated with each individual cell length if you wanted. You had an area associated with each individual cell if you wanted, right? Things like that, and a preferred area for each individual cell. So the first thing we're going to do is say, if we have what's called a homogeneous system of cells. Okay, so that means the model parameters are the same for every cell. Then the equation that you have from our lecture last time is much simpler. So the total energy is now the sum over all of those energies for individual faces of cells. But because the properties are all constants now, you can write it down in the following form. Kp Pf minus P naught squared. Okay, and so what happened, just so that it's not a mystery where any of this came from, is that we completed the square. So before we had something that looked like some sum over L edges. And what we've done is we said, well, if each of the surface tensions on each interface is the same, then we can pull out that surface tension. And then this actually looks like basically the perimeter of each cell, okay? The sum of the edges, right? And then we can complete the square because we have a term that's linear in P and a term that looks like P squared. And so this P naught you can find by completing the square. It's just, some that lambda over to gamma. And now in your old equation, you had a K bar, and I think I've taken a half. Okay, and this Kp is basically your old coefficient of that contractility term that showed up in the Farr paper. Okay, so hopefully not too much of a mystery. And actually, I would argue that from my perspective, this is actually a little nicer in some. I mean, both as a physicist, right? It's nice as a physicist. It's a simple equation. But also what it says is maybe I didn't have to know all of the specific biological details that I went through when we discussed the origin of that vertex model equation. Because instead, I can motivate this simply by saying, okay, I think there's some approximation of a mechanical work function so that cells are doing a lot of things to have a characteristic area, cross-sectional area they want to have, A naught. And then as a physicist, this is just the further penalty, this is the penalty away from that. So if I don't have any forces, if I have a system which is mechanical equilibrium, then this is the first order thing I can write down. And similarly, if the cells are doing a lot of things and they have a homeostatic perimeter that they want to maintain, then this is the simplest term I'd want to write down. And then I would say there may be lots and lots of contributions in the cell biology literature that could be used to justify a functional form like that. Okay, so Yeah. Yes, of course.
But somehow the surface tension or the line tension we had before is physically something very different from an elastic system. But now, by choosing the right term, we turn it into an elastic system.
So, well, what I would say is actually we've put the elasticity on the perimeter. So I would actually argue that no, just to push back a little bit, sorry, Ulrich. No, we didn't. There is still, I can always write this out. I can always expand this, and there is a linear term, right? And so what I have insisted is there has to be a quadratic. Well, I have insisted there's a quadratic term in P. It's not a linear term in P. So I should be okay. Actually, we're gonna be here, and I have a whole series of slides about what happens when you this energy functional, which of course is something we never do in physics. A and atom B have this interaction, and then I'm going to figure out its emergent behavior, right? And we're done. The right thing is to write down, and so I'm go through something which would be insane to most physicists, which is let's completely change the functional form of this object and see what remains. So we're going to do that later. Okay. Yeah. Yes. Okay. And you can tell me how you feel about it when we get there. Okay. So let's go to the next thing. Okay. So the next thing is that if you're a good engineer or physicist, you always want to non-dimensionalize everything, especially if you're going to simulate it, right? You simulate everything in terms of natural units, okay? So if you non-dimensionalize, then let's it by square root of A naught, which is a length, and something that looks like Ka A naught squared, which has units of energy by our formulation. Facets. In which I've been involved. These objects are sometimes called little p's, they're sometimes called little q's. It's hard because there's not enough letters in the alphabet. Here I'm calling them s's. It's a shape factor, okay? And so the idea is that this S naught, sometimes it's called P naught, sometimes it's called other things, is just the ratio of the target perimeter of the cells with respect to their target areas, square root of their target. And that's the whole point. And so this is an important quantity that we'll call the shape index or the cell target shape sometimes. And then this object here, Kp tilde, this is Kp over Ka A naught. It's the dimensionless ratio between the moduli. So I'll call that a moduli ratio, the perimeter modulus and the ratio modulus. Okay, so then if we want to look at this system, because right, this still is two quadratic penalties, right? It's two quadratic terms in the energy functional. So if I want, this energy functional gives rise to two constraints on each face, right? And it's exactly of the functional form that we already studied. It's quadratic. So if I want to have a, so I change this variable because this is the target shape a cell wants to have. And if I made this target shape exactly equal to that of a square, I would make squares the target thing, like a perfectly symmetric square. But like if I wanted to make it a pentagon, I would make it 3.81. And if I wanted to make it a hexagon, it would be 3.72. I changed this variable and I changed the shape I want to have. Great. Good question. Okay, so there are two on each face. Okay, and that means that if I want to do constraint counting for this system, I want to see if Maxwell-Caledine constraint counting can explain rigidity. I have d times the number of vertices is the equal to the number of degrees of freedom in my system, right? Number of constraints, which we've called m before, that's equal to 2 times the number of faces, which is, and you can work this out for yourself if you want, is 2 times the number of vertices in these types of basic network structures. And so here, we hold for why that is in 2D. Model. So X model. And this equals 3 for a 2D vertex model unless strong anisotropies. Okay. And so if I plug is the number of degrees, which is 2 times n. Okay. Using the terminology that we developed over the last few lectures. Okay. Good. All right. Okay. But if you simulate this system, you find that there does, in fact, a rigidity transition, and there exists precisely one, well, actually, that's, I'm actually simulating the model without the area term, and it still works. So that's another change to the energy functional you can do. In that version of the model, there's one state of cell stress at the transition. In this version of model, there's actually 2 states of cell stress, but you can show that they're orthogonal to each other. And so it's still I'm approximately telling you the truth. Let's assume that there exists one state of self-stress at the transition for vertex models. Sometimes there's 2, but the second one is very simple. It's a gate associated with the area, okay, at the transition. And so you basic a situation very similar to the spring network, so similar to the spring network. You basically find, if I make a plot of the shear modulus function of S, this is G, I basically get a straight line that terminates at some S naught star. Values of S naught that are greater than this, then I have a basic modulus. There's no finite cost to deformations. And I have a solid. And it is precisely the same physics as strain stiffening in fiber networks. Okay. So, oh, one more thing and then I'll go. So this theory 3.8 and but that's actually another lie. So sorry, everyone. Maybe some of you are familiar with the jamming transition. It turns out that there's actually a range of densities at which the jamming transition happens, not just one number. And there's some really interesting and subtle physics as to why there's a range over which a transition happens in a control parameter. And the same thing happens here. Actually, there's a range of S naughts over which the transition happens. And it actually depends on the disorder in the packing. There's this interesting thing. And so I'm happy to go through a lot more details, but I'll just for now put a little squiggle here that says actually there's a little bit of subtleties in this. It's certainly what I said is largely true, but there's like a range of transition points and it doesn't disappear in the thermodynamic limit. And that's disordered systems actually, including Jan systems. Question? Okay. Yeah, and I can also try to move it to this side. Yeah. Okay. Yeah, it's sort of hard because I'm wearing weird clothes for it, but okay, maybe I'll try this. Yeah, yes. Thank you. Oh, so it depends on whether there is any pneumatic order. So I will talk to you, actually, I'm going to show a slide about that in a second. So this result is for an isotropic system where there's no pneumatic order. And so it explicitly depends on the target shape of the cells, which is the model parameter. That's the model parameter I'm switching. And then in a moment, I'm going to talk about what happens to the observed cell shapes across this transition too. Okay, cool. Yes, from computer simulations. Yeah. So very explicitly, we went over a derivation of why in general you have threefold coordinated vertices. Okay, so that is sort of something you see very clearly in isotropic tissues. If you change the connectivity, then actually the diagram looks a lot like the one we showed you for the fiber networks, where actually you can also go along the connectivity axis. And actually Max B has a really nice paper where he shows that in certain systems where you do have anisotropic tensions and you actually increase the connectivity of the network via those rosettes we talked about, the scenario is exactly the same as increasing the connectivity in fiber networks. But there's a generic reason to think that most tissues, for sort of a very standard reason, sit at z equals 3 in 2D. Yes.
So you have a 3-4 coordinate
Vertices are 3 coordinated. Yep. And that is actually, when I said where this transition happens depends on the degree of disorder, that's exactly what I mean. Disorder in the number of sides of the polygons, because in 2D, of course, you have that tiling variability. And I can talk to you very extensively about that detail, but it's a little bit involved.
I think of it as a regular or
Random. You basically, and so I would say it's just like, it's a little bit similar to the jamming scenario where for a while, I don't know if you remember, but people were talking about like maximally random jammed. You find 3.81 in the limit that you try to make the system maximally random. And as you build, as basically you get rid of pairs of 5s and 7s and you make it more and more ordered, then you get you basically go sort of continuously to the transition point for an ordered system, which actually occurs at 3.72. So there's a whole line, just as in jamming, there's actually a whole line of transition points. And where in this number at which this transition happens depends on precisely on the degree of disorder. Yeah, yes. I mean, all of them. I mean, all the math I talked about is independent of what the actual features of the incidence matrix are. So this theory describes both, ordered and disordered systems, if you will. Yes. Yes. Yeah. No, that's a really good question. And that's why I didn't talk about it actually, is because it just shifts the stiffness. It shifts where this line is, but it doesn't change the feature of where the transition is. Really good question. Okay, so now I'm going to switch to some slides, I think, and we'll be on slides, I hope, for the rest of today, unless there's questions that you want me to answer on my notes, because I wanted to give you some ideas of applications of all of this jazz. Okay, let's see if we can get you up. Yay, okay. So I want to show you some examples of vertex models in real life. Then I want to try to get at Ulrich's question by talking about universality of vertex models for the rest of today. And then I'm going to think I don't know if we're going to get to this, I hope we will, to think about how you can actually use these ideas to design mechanical metamaterials. Okay, we'll see if we get there. Okay, so the first thing is I just wanted to show you a picture just of because I'm bad at drawing these things on the fly, right? These are sort of different values of this shape index, the perimeter to area value, right? So if I have larger values of the perimeter to area, those kind of look like pancakes or something. And then I get more and more rounded. And if I'm a perfect hexagon, I have a value of 3.72. And so one of the things you can do in simulations is, for example, you can change the value of the target shape index in your simulation along this axis. And then if you have a small finite set of fluctuations in your system, you can ask, for example, how often do cell neighbors rearrange? And if I put any if I'm floppy, it turns out in these systems, and I put finite fluctuations in the system, then I have a 0 modes and I'm allowed to move around, and I actually switch neighbors and change neighbors. And actually, I'll show you in a minute, have the rheology of a fluid, which is nice. So all we did was the 0 temperature dynamics, which is floppy to rigid, but you can do an extension, a simple extension of this to finite temperatures or finite fluctuations, and you get kind of what you would expect. Okay, and the reason I'm showing that is because then this is work now from 5 years ago almost, where we looked at fruit flies. And I have to tell you one more thing, and I'm not going to go through the details here because it would take a whole lecture and I think it wouldn't be that exciting, but it's actually related to some of the things that are talking about pneumatics and active pneumatics. So the idea is cells can also have their long axes be aligned. So once I have a cell that has a long axis in its shape, it's possible for that long axis to be aligned. And it turns out that everything I told you occurred along this axis where there was no anisotropy, and the cells have no pneumatic alignment. Okay, but then I could say, well, actually, and it turns out in fruit flies, this is really important, there is anisotropy, and we characterize it using, basically this is a pneumatic order parameter with one small difference, that it's also multiplied by the magnitude of the long axis, because the magnitude of the long axis can change. So it's just a pneumatic order parameter generalized to molecules that could change their shape, if you will. So it's the natural pneumatic order parameter when you have molecules that can change their shape, okay? So that's what this is, but you can just pretend it's the pneumatic order parameter if you like, okay? And so what we've done now is, because fruit flies are awesome, we can look at convergent extension and we can extract all of the shapes of all of the cells, and we can compute both their shape index, which is just the observed perimeter to square root of area for each one of the cells in the embryo. And we can compute well, not in the entire embryo, we're looking at a patch in the embryo, which is undergoing convergent extension. And then we can also quantify basically the cell shape alignment Q. And oh yeah. All you do, so there's two things you can do. So either the Hamiltonian is exactly the same and you just strain the box, so you have a shear degree of freedom and you strain the box, or you can actually change the Hamiltonian and add basically extra tension along interfaces that are oriented along a certain direction. Interestingly, both of those things give you exactly the same answer. So it doesn't matter for this result which one you do. And so the short answer is no, you don't have to change the Hamiltonian to get this. You can just shear it. And so basically the cool thing about this, the reason that I really like this image is basically this black line was predicted a priori with no fit parameters from vertex models. So we needed numerics to tell us where, because I told you there's no theory for where this point hits down. So numerics told us where this point hits down. This curve is basically a direct result of second order rigidity theory. So this is a quadratic curve, and it predicts that it should be quadratic. But the key thing is that actually we drew this before we got any experimental data. Okay, so there's no fit parameters. And then what we did is we took all of these embryos. So I think this is data for maybe 10 embryos. And we traced out trajectories over time as the embryo was developing. And we measured how often cells changed neighbors between two time points. So this is a trajectory for a single embryo. And what happens is you can see it starts out in the solid phase because it's blue. There's basically no rearrangements. Okay, it starts out in the solid phase and it kind of goes way into the solid phase. And then it kind of starts to go back in this phase space, and there's basically a critical point at which all of a sudden the rearrangements turn on. And, in this particular embryo, it also happens to be at this point which intersects our a priori prediction, right, of where it should happen. And actually, when you fill in the lines from all of these embryos, You know, it's kind of amazing, right? That the blue is all on this side of the, not all, but mostly for biological data on the solid side. So where we predicted the thing to be solid, it's solid. And where we predicted the thing to be fluid, it is fluid. And so I think this is a really nice example. Now, there are some problems, and I'm happy to discuss with you, and like I've discussed with many of my colleagues, like there are some interesting subtleties here. For example, like Bohr-Schreiman's group has demonstrated that you would think if it were truly a fluid phase here in the fluid phase, that the cell should be changing neighbors really rapidly and there should be no patches that are solid-like. But that doesn't really happen. It actually is more like a very, like a what's called a yield stress solid. So it's sort of still a little bit solid-like, even though it's very plastic. So kind of like mayonnaise, right? You spread mayonnaise out, but mayonnaise is secretly a solid, right? But it kind of looks like a fluid when you're spreading it, okay? So there's some subtleties, but what I would say is this, in my opinion, is remarkably good for a very simple model making a prediction for dynamics in tissues. And so it suggests that there's something, to me anyways, I mean, I'm biased, of course, this is our work. I think it suggests that vertex models really are a reasonable model to predict real quantitative features of these tissue types, which is nice. Okay. There's also, I'm going to go through this really quickly. There's also some data in breast cancer cell lines. So this is some work we did with Joseph Case a while back. And I just wanted to show you, you know, if you have things that are crossing a fluid-solid transition, then one really nice assay to check whether it's happening is these fusion experiments, tissue fusion experiments. Because if I have things which are fluid-like, then the thing will round up into a ball, right? That's good. If I have things which are solid-like, I'll have elastocapillary effects where they kind of like attach a little bit because they're soft, but then they don't keep fusing. And then I have this weirdo situation where it kind of partially fuses and then gives up a little bit. And you can ask, okay, can I basically use cell shapes to, and I'm actually not going to go through any of this data, it's published, but it seems like there is a, like in these sort of systems that kind of like half fuse here. I'll play the movie again. Maybe I won't play the movie again. In the systems that half fuse, they sort of have a gradient in, we think, the fluidity from inside to outside in those aggregates, and that matches with cell shapes, and it predicts like which part of this tissue is fluid-like and which part is a solid-like core. So that's kind of neat. Okay, so it sort of is useful in that. Okay, so you know, now is kind of like the big question, I think, is like, this model is stupid in some sense. So like, why does it work at all? Okay. And I'm going to tell you about our attempts to ask whether maybe the answer of why they work is because this type of rigidity transition is universal across a very large class of models. Okay, because if that were true, it's just like universality and other physics problems, right? I don't have to get the details right in order to make a prediction about certain features of an experiment. In fact, I can get almost all the details wrong and I can still make a prediction, right? So that's the question we're trying to ask, or the framework we're trying to put this in. Okay, so like I put these in capital letters, right? Because like, again, physicists never do this, right? We're going to explore what happens when I make changes to the functional form of my interaction potential. So let's say I have the standard vertex model here, which is in this paper. And again, we said we could write it out this way if we wanted to, if we didn't complete the square, right? And the first thing you can do is you can say, well, what if I just get rid of this squared term? Right? If I get rid of this p squared term, I just don't believe it exists. I don't do this anymore. I get rid of this p squared term. And so now I'm left with something that looks like an active foam model. Okay. And there's a couple of papers that have this type of model. And the first thing you realize is that this model it's pathological in two limits. So there's one limit where I basically get collapsed polygons. And that's because basically the surface tension wins out over this area modulus. And so you basically can get the smallest surface area possible by collapsing all the polygons and making one big soap bubble. That's a good way to minimize your lengths, okay? And that's this phase. And then if I basically go to where I have basically a zero line tension in this model, then I also get an instability, and that one's also completely obvious because I can increase the length of all of my interfaces with no penalty, right? So then I make starfish, or I make, very long, crazy cells with lots of fluctuations to them, and that's free, right? So why not? And so what I'll say is that by adding this p-squared term, one way of thinking about what we've done is we've enabled ourselves to sort of study perturbations around this point. It's one way of thinking about what you've done, okay? And so you can ask, well, what is the mechanical behavior of this system? It has no fluid phase. It's always a solid. And you can say, well, what is the mechanical behavior of this material in its solid phase? And in order to think about that, we're going to have to think about I would say you can look at the finite frequency response of it, for example. So I'm going to tell you about that in a second, but this is the critical features of this change to the energy functional. So let's call that model 2, okay? That's model change 2. Okay, then we're going to do some other model changes. So the other model change, let's say I didn't want p minus p squared because I thought that was total BS in the first place. And instead, I thought every edge has a rest length that it wants associated with it. Right? That could be another thing I do, and we'll call that the spring edge model. So now I don't have constraints on individual, on perimeters. And this is, Ulrich, this is your like, I really went in there and changed the number of constraints a whole bunch. And I really don't have a surface tension anymore. This is like when the edges are little springs and not tensions. Okay. But then I could say, well, actually, that's already not what's reasonable for a real tissue, and work by some of the people in this room. So this is some work between Shiladisha and Margaret, and then this is out of Roy Schreiman's group, says, well, actually, in real life, the rest length of these edges could potentially be set by like recruitment of myosin to these edges, and also the activity of like associated molecules, like rho kinases and stuff like that. And so there's a bunch of rules. This is the one from Null, but there's a beautiful set of rules in Statin too that sort of say, okay, like maybe when the length gets below a critical threshold, then I have a response or something. You can put in all sorts of dynamics on this L naught, and actually also on the Ks if you wish, to mimic all of these dynamics. Okay, so we'll call the raw model, this one, spring edge model. Then there's one with extra dynamics that has myosin recruitment. We'll call that active spring edge model. And this is a different one that I'll call an active tension model. So let's call those models 3, 4, and 5. Okay, yeah. Okay, and we changed the energy functional a lot, including adding active dynamics to it, right? Okay, yeah, okay. So when we do that, we get the same answer. Okay, isn't that neat? So what I'm showing you is the behavior of the shear modulus as a function of the relevant control parameter for that model. In the standard vertex model, it's the shape. In the spring edge models, it's the length of the spring. And in these systems that have myosin recruitment, it's like some crazy thing, but it's something you can write down. There's a control parameter for it, okay? And they all basically have this same behavior of the shear modulus that transitions at a critical point, and then it's flat, and they become floppy. So this rigidity transition happens in all of them, number one. Number two is that actually, this is crazy to me, the observed cell shape index, which is the obvious variable to look at for the vertex model, right? I'm showing you that as this on the same control. And the cool thing is that it actually works in these two models, which it has no business working in. Because this is not the right control parameter for this transition is the length of the edges of the springs. Okay, so that's interesting. And it does suggest that, and I'll come back to the why question in a moment, but like, okay, that suggests that this is a universal feature of all of these types of models. Okay. Oh, and this is what happens if these two versions, you can change, there's a parameter, which is the myosin recruitment rate that you can change. And so it's kind of cool because the myosin recruitment rate, it turns out it just changes the stiffness, but it doesn't change the scaling. Yeah.
The models that you don't have like the P naught defined, so how you define the shape index is the actual geometry of the cell?
It's the actual observed geometry of the cells. And that's a subtlety which I'd be happy to talk with people after the lecture. It's a good order parameter for the transition in vertex models. We've shown that. Yeah, but it's there's a difference here, and I'm losing a subtlety, which is there's the target shape index, which is the control parameter, and then there's the observed shape index, which is just an observable that happens to be a good order parameter for this transition, which is maybe not so surprising, but it's kind of surprising. It's also a good order parameter for the transition for those two. Yes.
In all of these plots, it looks like, with the exception of the changing myosin recruitment rate line, it looks like G goes linearly.
Yeah. Yeah, it's true. And it's even true down here that this minus in recruitment makes the functional form away from the transition, not linear, but actually as you approach the transition, it's still linear as it goes in. Yeah, it's also, yeah, well, it's an interesting universality. Yeah, it is a linear scaling and Y is interesting. Yeah, yeah. Yeah. I asked you to be a ringer for the, yeah, I basically seated you in the audience to ask that question. Yes? Yes, but it's not a surface. So you're exactly right. So first of all, yes, what you said is essentially right, but it's not necessarily a surface tension. And normally in physics, if I change the dynamics of like something from being a spring to being a tension, that has an important consequence for its mechanics. I'm looking at Ulrich because I hope he would agree with me, right? Like in general, like he just told you that if I have a surface tension like situation, that's very different from a elastic spring like situation. And I literally just changed that and I got the same result. Yes. Yes, so that is a very good question. So the short answer is measuring the critical exponents for these things is really, really hard for reasons that I can tell you. So we've tried to do that a little bit. Actually, so an even simpler model than any of these is spring networks, under constrained spring networks. And actually there's some controversy between multiple groups in the field as to what the critical exponents are for that system because of various challenges numerically. So I don't know that. So that's why I'm being a little bit, because right, the gold standard in physics is that I want to claim this is critical. I'm like, this has the same universal scaling exponents, and here they are, and they're related by these equations, right? And I'm not doing that because I actually can't. But what I am doing is doing something that's a little bit, I am saying there are universal features. And actually, I'm going to show you that for the rheological finite frequency behavior, we can get scaling exponents, and they're the same. Okay, that's what I'm about to show you. Yes. Yeah. So we and Fred McIntosh have competing ideas about how to do that. So the short answer is, okay, what you would normally think to do is think about like fluctuations of features near the critical point, right? So you basically could go in and you could say, okay, what is the scaling of the shear like what is the critical, like what is the exponent that describes the shear modulus when I change the control parameter right when I go towards that critical point, for example. You could also look at basically fluctuations in the response. So I basically push the system a little bit and I look at the scale of fluctuations. Yeah. So and what's the fixed for? Yeah, yes. So can I just say that is complicated and under debate. And I would be happy to show you the papers where we've started to try to work this out as a community, and it's not settled yet. Yeah. Okay. Yes. Yes. They always have much more heterogeneous areas. So it's kind of interesting because like also once you do this type of analysis, you can also ask what isn't the same about the models, right? And actually the area fluctuations are not the same. No, that's one of the things we write in this paper that someone should go and do as a way to test model. But it's a little challenging, actually. Let me just like to be a little bit more clear, because actually once you get into the solid phase, they actually kind of all look the same. Okay, and so a lot of tissues are more in the solid phase that are easiest to do this with. And so then it's like in the floppy phase, they're really different. Okay, in the solid phase, they're more similar. So it's, you know, I don't know. But it's something someone should do. Yeah. Okay. Finite frequency response. Okay. So Ulrich gave a really nice introduction basically to Maxwell models viscoelasticity. And he focused in his lectures on basically if I sort of pull on something, you know, and I just keep pulling it, right? Okay. Another thing you can do if you're interested in doing a rheology experiment is you can oscillate the thing, right? And so this is an oscillatory rheology experiment. And so, you know, what you do is you can measure the stress. You can do either way, as Ulrich already said. But what we're going to be doing here is we're going to be shearing the material back and forth. So we're going to be giving it a shear gamma. And then we're going to be measuring the stress in the system, which we can do because we have a U, right? So we can compute the stress. And so if these two things are basically in phase, because then the stress, well, actually, I think I have a slide on this. Okay, so here's the things that Ulrich already introduced, right? These units with these basically rules for how things go together. Okay, and so if I have a maximum, you've already seen this. This was worked out. I'm going through it super fast because you just saw it. Okay, then you can sort of think of this, and there's a characteristic time scale in the problem, and you get this relaxation behavior. Okay, but if you have a dynamic load, okay, like this, to a model like that, basically you can write out what sigma does, right? It looks like this. Okay, and then I can think about the parts of the system that are basically in phase with my driving or out of phase with my driving. Okay, and so if I want to sort of think about the part which is in phase with the driving, that's the part where the stress is proportional to the strain, right? So that's the elastic part. Okay, and if I take an oscillatory shear and I take its derivative, right, then that means that if I want something proportional to the strain rate, it should be 180 degrees out of phase, right? It's the derivative of that. If I have a cosine, the derivative of it is the sine. That's 180 degrees out of phase. So the part that's out of phase, that's the loss modulus. It's the fluid-like part. Okay, that's the key idea. Okay, great. Okay, so people call this G prime and G double prime, and so it's all over literature and soft matter, and also biology experiments are starting to be able to access it. And I'll just show you a simulation. You can do it in a vertex model. You know, we code up this model on a computer and you shear it, and this is what you see. Okay, cool. Okay, this is what the standard vertex model finite frequency response looks like. And we're not the first to do it. There's a paper that came out actually a couple years ago now by a bunch of folks, including Rasko Skepnek and Andrei Kazmirlaj, that already said this. But okay, this is the results. Basically, if I'm on the, you know, I showed you a shear modulus, right? And I showed you there's a range of parameters for which the zero frequency shear modulus is a solid, and then another set of frequencies for which it's a fluid. Yeah? Yeah? Okay, so now I'm going to show you, for all the next few slides, I'm going to have a top box, which is our analysis of the behavior of the system in the solid phase, and then a bottom box, which is the behavior of the system in the fluid phase. And by fluid and solid, I mean the ones defined in the zero frequency limit. Yeah? Okay? And then I'm going to show you the frequency. So this is changing the frequency of the system. Okay? And so and this is like for those of, if this is like sort of your crash course introduction to rheology, like if you look at gelation or rheology papers, they all look like, they're basically just a whole bunch of plots like this, right? And so what you see is that the solid markers are the storage modulus. That's the solid part. So solid is solid. Okay? Okay? The elastic part is solid, okay? And the empty ones, those are the fluid or loss modulus, right? It's the loss modulus. It's what's happening to the fluid component of the response, okay? So in the solid phase, it's good news. You see that if I basically go to the zero frequency limit, I basically have a flat curve and it stays really high. So that means the storage modulus dominates at low frequencies, which means it's behaving like a solid at low frequencies, which is good because we said it was a solid at zero frequency. And you can learn more information. You can ask, well, what is the behavior of this basically? And this is, you see that it's scaling pretty nice and robustly as linear in omega. And this is actually what's called Zener's model for solids, and there's a homework problem that I gave you about thinking about what this, and I've shown you the spring dash plot model using those elements that Ulrich introduced for Zener's solid model. That's the model that generates omega goes to zero here and linear scaling for the loss modulus. Okay, so not only did we learn that this thing was good. It was a solid even at finite frequency, but we understood like what type of approximate viscoelastic model matches it. Okay, and then in the fluid phase, basically you get a behavior which is where at low frequencies, the loss modulus is the largest thing. So it's linear, but it's always bigger at low frequencies than the storage modulus. And so that tells you this thing is basically behaving like a fluid at low frequencies, which is good because we said it should be floppy there and it's fluid away from the floppy limit. And then you see omega squared for G prime. And it turns out that this scaling is consistent with Berger's model or the standard linear liquid model. And again, I gave you a picture of the diagram for your homework problem. And this is basically a standard model, viscoelastic model for fluids. Okay, so that's neat. So now we understand both that our zero frequency analysis carries into the finite frequency range, and we know its behavior, and we even know its scaling. So now we can ask, what is the finite frequency behavior of all those other 6 models or whatever, the other 5 models I talked about? So the foam model, it's only stable in the solid regime. So I'm only showing you data from the solid regime, but it has exactly the same scaling at low frequency. It has omega here and 0 scaling here, which is the same as this solid, basically. Although there's some really interesting behavior up here to this model, which you see a hint of here, and it's stronger here, and we don't understand that. So somebody in the audience, if you're interested, come talk to me about it. I don't know. I don't understand it, okay? But I would say the low frequency response is clear. It's just like this, and it has the same scaling. Okay, the spring edge model, exactly the same scaling, except down here at the super lowest frequencies. Why is that? Well, because if we're going to be really honest about a spring edge model, the area elasticity of the cells basically eventually acts a little bit like a bending modulus. And so there's really nice work by a whole bunch of people in the community saying that if I have a little bit of a bending modulus, then constraint counting tells me that when that bending modulus is important, because then I have extra constraints basically on the edges, that those things come into play and I actually get a solid-like behavior. Okay, so what you're seeing here, this turnover, we understand it. It's basically coming in at the very, very lowest frequencies. You basically get a finite modulus down here. And that's actually, I didn't show you, it's perfectly consistent with what the shear modulus calculations do too. They don't go to absolute 0, they just go to a very small number also. Okay, so it's the same, and it has the same scaling. And then the active spring edge model, also the same scaling. Okay, so that was a ton of work in like 3 slides. So Sajjad Arsash, who's the guy on let me show you his picture again, because this was like a completely heroic effort by Sajjad, and he's awesome. So Sajjad did all of those numerical simulations I showed you and also understood what they were saying. And so good job, Sajjad. Okay, so, okay, let's go back. Yes, the conclusion is, yes. Yeah. Yes.
Does that rate of resting?
Yes, it does. So there's a lot of details, but actually this is important. So let me say that, okay, in systems that have extra dynamical equations on the degrees of freedom, like you expect in biology to have, you have the same problem that you have in, say, gelation, where you're going to have aging, right? So you're going to have a history-dependent dynamics because you have this internal dynamics like the tension remodeling timescale. So the way we're handling that for discussing universality here is that we change the waiting time that we wait. So this is a standard method in gelation rheology where you wait a certain amount of time and then you measure what happens to the system at finite frequency. And you see that actually there can be a change in this behavior. And so actually it turns out that this waiting time is really, the features of this waiting time are related exactly to that dynamical time scale. Yeah, and we can talk more. Yes.
Yeah.
Probably, yes.
Well, but then some model, in some cases, you have like a linear, you have 2 models in both of which you have a linear, the imaginary part, but then have different real parts. I'm a little confused how that.
I actually think that because all of these, depending on how you put those springs and dash pots together, you can get various scalings for these omegas and omega squared. And all of those spring dash pot models have to obey a Kramers-Kronig relation because they're just the relationship between the real and imaginary parts. Okay.
You know, how can the unique relation, how can two models have the same imaginary part? but different real?
Oh, no, I don't think I'm saying that because so the real, this is one real part and one imaginary part, right? And actually, if you look at it, so I have an omega here and a zero here, and in all of the models have that relationship. When this is omega, that's zero.
That's constant.
Yeah, yeah,
You had a model.
yeah. And actually, maybe I'll stop because like I haven't thought about this question at all. So let's chat about it. And I don't know the answer to it. But I guess the key thing I want to tell you for this result is I don't think anything I'm showing you actually is inconsistent with even that, even though I don't understand the details, because I'm actually showing you they're all the same. The relationship between the imaginary and real part for all of these models is the same. Yes. Yeah, that's a really good question. So the short answer is this is a new idea. So folks haven't looked in lots and lots of tissues, but there are lots of tissues where people have started to look for this, and almost everywhere people have looked for it, they have found it. And so like I gave you some examples, like zebrafish tail bud tissues, zebrafish shield stage tissues at a totally different stage. Both of those are near a fluid solid transition. Fruit flies are near a fluid solid transition, right? During conversion extension. And you know how I started this whole thing by sort of saying, hey, if I need to have something that sort of has large scale deformations, then I need it to become a fluid for a while. But if it needs to be an animal, it needs to go back to being a solid so it can support shear stresses. I think there's a real deep reason actually why biological tissues are tuned that way. And I think there may be some tissues for which, and actually let me give you an example. The amnia serosa is a tissue inside fruit flies. I don't know how many of you work on fruit flies, but actually which stays solid for its whole life. And actually, I mean, I'm making this up as a physicist as a just so story, but clearly what it's doing is it's acting like a rubber band that actually pulls on another tissue to help elongate it. And so it behaves like a solid the whole time. And I think there's a reason why it behaves like a solid its whole life. But I think there are a lot of tissues that have this capacity to be tuned near a fluid solid transition precisely because animals have to be actually like okay, I'm sorry, I'll say one more thing. And okay, plants, the way plants get different shapes is they grow because they have cell walls and they can't rearrange anything. So strain isn't an option. So for plants, you just grow things. Like if you want a shape, you grow it. Maybe kill some cells too while you're at it, right? But kill and grow. Animals seem to have a different developmental paradigm where they actually shear the heck out of everything, right? They actually have huge deformations. They make a ball of cells because they don't have cell walls. And so like cell rearrangements are pretty easy to facilitate, I guess. And so they have this different paradigm where they sort of stretch and deform a lot. They like make a ball of cells, they differentiate it, and then they sort, and then they stretch. Okay, and in those tissues, I think it's reasonable to think those are pretty often poised near a fluid solid transition. Yeah. Yeah, that's really cool. Okay, and so I think Andrea Liu is going to talk about this next week because we've been collaborating on a project to try to figure out, okay, because not only in order to get something to move, like just like, okay, let's go back to that glass blowing analogy, right? Like I can change the temperature and change the rheology of, my glass blown fish, but unless I apply a force in exactly the right spot at the right time, that change in rheology means nothing for the shape, right? I also have to apply forces. Okay, so how do I think about exerting control on a system where I can both have control over the rheology and potentially have control over the localized applied forces? And so I think physical learning is a really useful way to think about that problem. And Andrea, I think we'll talk about exactly that next week. Yeah. Yeah. Yes. So the short answer is if you take this system and you put it in, because actually, okay, how much detail do I want to say? Okay, In disordered systems in general, not always, but often, there's a relationship between the curvatures of the potential energy landscape, which are described by the shear modulus, and the height of the energy barriers between metastable minima in a disordered system. So the less curvature there is, the lower the energy barriers. Not always true, but often true. So what happens actually in some tissues is that instead of going all the way to the fluid where the energy landscape is flat, what we think sometimes they're doing is they're going to kind of close to it so the curvatures are low, and then an applied force can take you over those low energy barriers. So the reason I'm going through that is because that I would call plasticity. So it's a low yield stress solid that has plasticity that connects you between states. The alternative is you're really a fluid and then it's zero energy to transition between states. So I think there's an open question as to whether these systems are always in the fluid phase or they're in a very low yield stress solid phase. And then there would be plasticity. Yeah. Okay. So I'm going to say a crazy thing and then we can do something else. Okay. So let me say the crazy thing, which is, yes, what I just showed you a while back now, but thank you for all the good questions, is that there is a rigidity transition across many models. It's predicted by this cell shape parameter in both zero frequency and finite frequency response. That's what I showed you all those slides about. Okay, so in small letters, the question is like, why? Okay, so this is where I say the crazy thing that's open, but here's the crazy thing. Okay, so I think it might be because it's a second order rigidity transition. Okay, so second order rigidity, one way of framing what it says is there are two length scales in the system. Okay, one of those length scales is the number of cells or vertices per unit area. Okay, the other length scale is the characteristic distance between two cells or vertices defined by the energy functional. So for example, this unit is like L naught for a spring model, or P naught for a cellular, a cellular model, okay? This thing is like literally, I just put a certain number of cells in my box, right? And then I can get a length scale out of that, okay? Second order rigidity happens at the special point in configuration space where these two things can't be satisfied. That's it. You can go back through your notes and sort of see why that framing works, but it's true, right? It means because it's a geometric, so many of you have come up to talk to me. First order rigidity is constraint counting. It just matters the topology of who's connected to who. The cool thing about second order rigidity is it's not topology, it's only geometry. And so if I have a geometry that's specified by the number of cells in the box, and it's not commensurate with the geometry stated by my energy functional, which is like, L naught, then I can't make them both happy at the same time and I cross the critical manifold. That's what's happening. It's one way of framing what's happening. Okay, so the states that are compatible with both the energy length scale and the density length scale disappear. That is a very general framing of the problem, okay? And so the suggestion that's a little crazy is perhaps cell shape is a dimensionless comparison of these two length scales that sort of works across different models. And therefore, it generically describes the point at which these states disappear. That would work if that were true. Now, how to make that more precise than the wishy-washy statement I just said, I don't know, but it's a suggestion of why. Okay, it's a suggestion of why I think this works. It's because it's a second order rigid system. Okay, yes. What I mean is that if basically so I basically mean that okay, let's use spring networks as the example while I talk about this. So spring networks have an L naught. Okay, you can ask, is there a set of states with a certain number of vertices connected with a certain sort of characteristic incidence matrix? Is there a state where all of the L's are allowed to be basically equal to L naught? That's a compatible state where all of the L's, the actual L's in my system, are equal to L naught. That's compatible. If there's not such a state, in other words, I have to start having L's that are longer than L naught, or short, yes, well, it depends on the system, but longer or shorter than L naught, depending on how you're thinking about it being under tension or compression, then I get an angry system that is unhappy because there's no states where those two things are allowed to be the same. Yeah, that's the idea. Okay, yes. Yes. Oh yeah, it's a really good question. There's so many good papers out there, and I think Ulrich has just written one about what happens to systems on curved surfaces and how it changes basically both the sort of transition point for the systems and all sorts of other things for the there's a whole bunch of, you're exactly right. I'm assuming a flat surface, and curvature changes all of these things, and it's cool how it does it. Yeah.
Not so much today to sense the curvature, but there's this topological constraint between topological defects and of course will be a very important.
Yeah. Okay. All right. Okay. So maybe I'll talk about what one application of these ideas might be for designing materials in the last like half hour I have. Does that sound okay? Okay. All right. So, because I'm going to forget, the first thing I wanted to show you. So, okay, first of all, who am I working with? So this is Chris Santangelo and Tyler Haynes. So Tyler is a fantastic graduate student working jointly between Chris and I at Syracuse. And before I forget, I just wanted to show you that actually, I'm going to show you a bunch of stuff, but I know I'm going to forget to talk about it, but we're actually working with Ryan Hayward, who's here at Colorado, to try to make these things. So we're trying to design materials with special properties. And I just wanted to show you a slide that it's not just in a computer, like we're trying to make things. And so the key thing that you'll notice here is these are networks with exactly the same topology, right? And we've basically told Ryan and Joe, hey, could you make them with this exact geometry? Because this one we expect should be floppy for a while. This one should be rigid, okay? And this one we think we've optimized to have a large bulk stiffness and a small shear stiffness, okay? Using methods I'm about to talk to you about. And so this is very preliminary data. And of course, these are small systems and all the caveats. But it's kind of fun to see that, yeah, like if you just build these things, they have the properties that we've programmed in using some of the ideas that I'll show you later. So like we can say, because I think one of the challenges in designing like mechanical metamaterials is there's a vast design space for them. And you would like to have them have properties, actually, I would say very much like tissues. Like we already talked about how I kind of want to build Terminator 2, right? Even though that he's evil. But I want to build Terminator 2 because I would like to be able to make a mechanical metamaterial that, for example, can tune its stiffness by orders of magnitude with a small change to an internal parameter. So it can go from being floppy, where it can like scooch under a door, to being rigid, where it can like stand up and do some stuff, right? That's a thing I might want to be able to do. So what is, oh, go ahead. Oh, this is big. These are like hydrogen, this is like centimeters or something. This is not small. Because because we haven't included torsional springs in our theory, and we're trying to minimize the torsional springs. And eventually we'd like to not have them in the theory, but that's harder. Yeah. Oh, the same question. Yeah, and so we're trying to minimize the torsional springs. Okay, cool. Okay. So you remember, well, maybe you remember that we sort of the starting point for this is that we're going between bond space in a network. And here's the vertices. So I'm trying to use the same notation I used in the notes, right? So you have an equation in your notes that looks like this. And I thought I might draw a picture because it's much easier on a slide than on a piece of paper, because I mentioned there was this boundary matrix, and I wanted to give you a little idea of like how you encode boundaries in a system like this. So if you have periodic boundaries, it basically means that you sort of have a connection between one of these network pieces and an image of it. That's what periodic boundary conditions mean. And so basically this bond vector encodes all of those crossings across the box boundary. So this is just a picture of how you encode periodic boundaries. And if it's fixed, it's even easier. It's basically just you relocate the locations of each one of these to a point, and it turns out that that's a nice way to represent the boundaries. Okay, so this is just a picture to show you, this B thing is something that you can think about. It's pretty concrete. Okay. And the question we're going to ask is, can we make a new set of degrees of freedom that parameterizes the critical manifold? Okay, so I told you, right, that the critical manifold is all configurations. And of course, they have to satisfy force balance. And you want to have systems that have a state of self-stress, but you want the magnitude of that self-stress to be in the limit it goes to 0. So let me say that again, right? I said, okay, when we basically go across this critical point, right, we sort of start to have a state of self-stress, and those self-stresses are really important for the rigidity. We showed that because the rigidity depends on the pre-stress matrix, and the pre-stress matrix has that sigma inside of it. Okay, so one way of thinking about what the critical manifold is, it's the exact point in the configuration space where I start to have a state of self-stress, but it has zero tension in it. There exists one, but it's in the limit, it has zero tension. Okay, that's the idea. Okay, so then we have to figure out, okay, is there a way to parameterize this? And the answer is yes. Okay, and so we're going to internal stresses by coarse graining. This description is terrible, but it's correct. So let me say what it is. The lowest level degrees of freedom and to higher geometric quantities. Okay, so the idea here is that some of you asked, okay, what if this energy functional wasn't quadratic? Or what if the springs were like Hertzian springs instead of quadratic springs? Like what would change in what we described with the rigidity matrix? You know? And so here what I'm saying is, well, in order to get the rigidity matrix, we did this expansion, except instead of the H's, we had the F's. Okay, so what you have in your notes is this exact expression, except the H's were the constraints F. Okay, but now what I'm saying is actually let's relax that constraint slightly, and let's envision that we can pick H in a way that we want to make the math be nice for a given sort of set of constraints. Okay, and so if we want to do that for a spring network, it turns out that to make the math nice, we want to choose H not to be F, which, you know, so for a Hookean spring network, instead of choosing H to be F, we choose it to be this function of the lengths instead, right? So just to sort of write on the board, oh, let me put up one of these things so I can write on the board so I don't have to keep switching. Okay. So the idea is basically, and we don't need to turn this off, it's okay because you can see what I'm writing underneath of it. Should be really, the F sub alpha that we described for Hookean springs before was some K alpha times L minus L naught, right? So this was linear in, you know, L alpha, okay? This was a linear in L alpha. And it turns out that if you try to go through and do all of what I'm about to show you with this, things get gross, and they get gross because they're nonlinear. But it turns out that if instead you write an H sub alpha, which is proportional to L sub alpha squared, and you divide by 2 for mathematical convenience, then you just do all the things I showed you for F sub alpha, and it all works out the same way, except that instead of getting a nonlinear something at the end, you get a linear something at the end. Okay, so that was a little technical. But let's just do it. So we can define a new type of rigidity matrix, like sometimes I'll call this so the object that was df alpha by dxi mu, we define that to be r I or alpha. I think I did it the indices this way, I mu. Now we're going to define a new r, which has a little h subscript, and it's going to be dh alpha by dxi mu, where I can change what I mean by h alpha. That's all. Okay, that's the idea. Okay, so then it turns out when I do that and I make this choice, I basically get a linear relationship between this sort of constraints and things I understand. Okay, and it turns out that it didn't have to be this way. This is just a math feature, that it turns out that this object that sits here is our good friend, the pre-stress matrix, which we already defined in a previous lecture. So I'm saying we did some math. I'm not showing you the math. When you work out the math, this P sits here and it's nice, okay? So what this is saying then is that if you give me your favorite incidence matrix and boundary conditions and a state of self-stress, then I can use this particular, like having done for this particular choice of H alpha, I can basically give you the corresponding critical configuration. Okay, that means that I can basically say, okay, there's a state of self-stress, and I can basically map back to the configuration that has that state of self-stress. Okay, and actually I can map back to the configuration that has that state of self-stress with the magnitude of that state of self-stress being in the limit it goes to 0. So it's right on the critical manifold. I'm not showing you all the math. I'm trying to give you a flavor for it. Okay, that's the idea. Okay, so what does that mean pictorially? This is way easier than math. This was that horrible thing. Remember how horrible that manifold was that I showed you the picture of, right? This is in configuration space. So remember, this is the 3-bar linkage. This is configuration space for that 3-bar linkage. And this was the critical manifold, and it was even ugly for this easiest problem we can think of. When you do this mapping back and forth, you actually map this manifold in configuration space to this beautiful manifold in self-stress space. And so this is gorgeous. It's a sphere. Well, actually, it's a stereographic projection of a sphere, but it's basically sphere. And so that means that I can walk around in this space and go do all sorts of things that very easy in this space. Okay. And there's a mapping between the two. So once I pick this, I know this. And once I pick this, I know that. Okay. Cool. Okay. What does that allow me to do? We can rationally search the critical manifold for special configurations. Okay. So what we've done in the past, so let's say I wanted to take a spring network and I wanted to make it critical, right? I wanted to drive it until it was right at the special point where it was tunable between a fluid and a solid, because that's a nice property to have. The way I would do it is I would make a random network with this connectivity, and then I would strain it until I hit the critical point. Yes? Yeah? And then I get this network. As my children's preschool teacher says, you get what you get and you don't throw a fit, right? This is what you get. You're stuck with this. This is what you get. You're stuck, okay? It's cool. It's critical, but it's just like, it was determined by the initial geometry that I picked. Okay. The other thing I could do if I wanted a random network is I picked this incidence matrix, right? I generated it using, like, in this case, a Voronoi tessellation, because I wanted to ensure that I got an under-constrained spring network. And that's an easy way to get z equals 3. Okay, so I had a special way of making this matrix to make it under constraint. But another thing I could have done is I actually could have picked a random point in this space, right? Because each point in the self-stress space gives rise to a configuration. So I could sample uniformly in this space, and what do I get? That's another way. If I sample uniformly in this space, it's guaranteed to be critical. This is the critical manifold, so I've guaranteed it. So here's one example. I just pick a random point that I get from the self-stress space, and then I use my mapping that I created to go back into real space, right? Okay, I don't know, it's a thing, you get what you get, okay? It's another way to get what you get, okay? But let's say I wanted to optimize a large family of functions. I'm not telling you what it is, it's some objective function, and the key thing is that any objective function which I can write in terms of these bonds, these L's, I can always write basically that if I want to optimize O, I can write as a partial derivative as an else, okay? But because I have this mapping, I can also write it as an optimization over the states of self-stress, okay? So now we're going to just do that for a couple of examples. I'm going to show you pictures. Okay, so with this self-stress parameterization, I can basically search the critical manifold for states that optimize kind of anything I can write in terms of lengths. So one easy thing to write in terms of lengths is, let's say I wanted to self-assemble a network, right, out of units of the same length. So then I would want all of the lengths of all of my edges to be exactly the same when I formed it. And that when I formed it, I wanted it to be right at the critical point, right? I wanted to like make it, and then it would be perfectly at this susceptibility. And the question is, then I would want to minimize the fluctuations with respect to lengths in my final state. Another thing I might want to do is I might want to minimize the fluctuations in tensions, because let's say I have a network and the bonds have a critical fracture, right? They basically break at a critical tension, right? That's pretty common. So if I minimize the fluctuations in tension, then I have the thing that's most resistant to fracture. In that case, that's another thing I might want to do. Okay, so that's these two objective functions, okay? You can do it. Just using, I mean, it's literally like a couple of steps, because I can write those objective functions in terms of the states of self-stress, optimize in the states of self-stress, and give you the result. Okay, and the cool thing is that I did not expect this at all. When you do this for any, I shouldn't say any. For a very large class of networks that we looked at, you can always find one that has equal lengths. So you can basically, you can always find a critical system that's composed of equal lengths, which is very surprising to me, but you can always do it. So that means like, actually what we've shown is for a large class of incidence matrices, which you might think about encoding via like DNA linkers, right? You can encode an incidence matrix. You can basically make a system poised at the critical point where all the bars between the linkers are exactly the same length. Who knew? Like, I didn't know that was possible. And so that thing is really right on the edge of a floppy to rigid transition. So if you strain it a little bit, it'll be solid. And if you don't, it's going to be a floppy, right? That's a pretty neat property to be able to self-assemble, okay? Another thing we might want to do is you might want to, yeah.
Did you say something about tension fluctuation in those systems? Are those two related?
They are related. I don't think I have the pictures here. I have data. They're related, but they're not one-to-one. You know, so actually, I don't think I have the figure, but I'll show you a picture. Let me pause and I'll tell you something interesting about the statistics. Okay, so another thing you might want to do is use this as a design principle to maximize the bulk modulus or the shear modulus of your thing. So one thing to say is, in general, if I have a disordered network, its shear modulus in the thermodynamic limit is 0, right? And that makes sense because, like, you know, there's no, the symmetry of the problem is if I shear it this way, it's disordered. I shear it this way, I shear it this way. There should be no difference, okay? And so, but you can say, well, could I make a system with a finite shear modulus if I wanted to, even though it's disordered, and actually has exactly the same incidence matrix as a random network? I've just changed the geometry of it, right? Can I do that? And oh, how do you do it? Well, one of your homework problems was to demonstrate that by computing the normal mode, like you could write the shear modulus in terms of the normal modes of the Hessian. And so basically by sculpting the normal modes of the Hessian, you can sculpt the shear modulus. So that's kind of the point of one of those homework problems. And so we can maximize the bulk modulus of the transition. Here's a picture of that optimization. Okay, so this structure has the maximum bulk modulus. And here's where I get to tell you, Sheila, that this optimization is almost identical to the optimization that minimizes the tension fluctuations, which is perhaps very unsurprising. And you can actually maybe make an analytic statement about that. So this is almost exactly the same as minimizing tension fluctuation. Okay, but very different from minimizing length fluctuations, it turns out. Yeah.
Especially now, are these unique solutions or are they also whole?
That's so cool. Yes. So this one is has a subspace, which is Boris Schreiman has called isogonal modes. So there's a subspace of modes that's all related by having equiangles, but just growing or shrinking basically the network a little bit. So there, well, you can't shrink and grow everything. You selectively shrink some and grow some, so the area overall area is fixed. So there is a subspace of isogonal modes for this. There is a subspace of isogonal modes for this. There's only one this. This is unique. Some of them are unique, some of them aren't. And thinking about why that is kind of interesting. Yes, Carlos? Great question. It seems like I seated you in the audience too. Let me show you what happens under shear modulus minimization. Are you ready for this one? Woo! Okay, that last part is unphysical, right? So what's happening? What's happening is this system is doing the exact, right, it's doing the exact opposite of making things more regular, right? And what it's doing is it's basically picking certain bonds, and this is, by the way, the shear direction, right? That it's choosing to compress and putting the other bonds under tension. And that's apparently the solution. Okay, and so clearly if you keep doing this minimization, there is, for any finite size system, a state that you get, but it involves in a periodic box, like overlaps of the periodic box. Okay, but okay, the really nice thing about our method is, let's say, well, I don't want those. I want to find the system that has the maximum shear modulus, but doesn't have any of those overlapping extra edges. It's actually quite nice because those overlapping edges are ones that have sort of tensions that are opposite in sign to all the others. And with this nice, so this is my stereographic projection of the states of self-stress. You basically just say, I don't want any negative, or, you know, depending on your sign convention, I don't want any tensions of the opposite sign. And so basically this, I can basically say, okay, how close do I want to be to having zero tension in any of my bonds. We're going to parameterize by R. And of course, we can add that to our objective function. And this will generate realizable, physically realizable states. And then you do it, and this is what you get, right? Again, it makes perfect sense in hindsight. And these have a really nice finite shear modulus, and it has the incidence matrix that you specified, and it has exactly the material properties that you wanted at the end. And you can change exactly, like let's say that maybe Ryan Hayward can't make systems that look like this one because that's pretty, that's a pretty fine-tuned, you know what I mean? You can basically parameterize how weird you want these things to look by this R. Okay, it might be sort of as a proxy for being physically realizable. Okay, and so at the end of the day, now these are all systems that live on this critical manifold, right? So we're no longer like, we don't have to live in the mechanical space where you have just like one type of, like one type of system that becomes critical. There's a whole bunch of them, and you can find them, and you can also start to think about like, what are the subspaces that they live in of this critical manifold, things like that. Yeah. Oh, for a very low modulus. So let me be very clear, like all of these systems, by putting them on this self-stress manifold, they're all by definition right at the critical point. So every single thing I've shown you is at the critical point. And then we're saying, once I'm at the critical point, what is the space of things I can explore? So you can basically say, okay, if I'm at the critical point, what is the maximum bulk modulus I can have once I sort of strain a tiny bit? Okay, that's what you can ask. Well, you can optimize so that you're at the critical point, and as soon as you strain above the critical point, you have the minimum possible bulk modulus, like if I strain it a little beyond. If I put a dilational strain on this network, let's say I wanted to have the minimal bulk modulus possible after that. You could do it. It's just an objective function. So here I've shown you the maximal one because that's kind of nice, because it actually turns out that these types of networks actually have a jump in the bulk modulus so they go from having 0 and then there's a finite gap. And so you basically, I'm actually this one has as big of a jump as we can get. Like it's the maximum jump you can get. When you strain it, goes whoop, I suddenly have a bulk modulus. Yeah. Yeah. Okay. I think basically I'll just say a summary. So the summary is what this last little piece allows us to do is think about what is the space of states at this rigidity transition. And what we've shown is there's a manifold of states at the critical point, which we can completely characterize. And maybe I'll say one more thing. I don't know how many of you are interested in this sort of thing, but the fact that this is a stereographic, sorry, I thought I was closer to this picture up here. The fact that this is a stereographic projection of a sphere actually means that you can prove that in configuration space, the manifold of critical states is codimension unity. And I mentioned that before. So the fact that this is a stereograph, you can prove once you know that that's true. What that means is that I have my configuration space of my x's, and I can ask, what is the space of states that are rigid in this big configuration space, this high dimensional configuration space? And it's codimension unity, and it's a smooth manifold almost everywhere except at branch points. And so what that means is like any generic trajectory in the space is going to hit that manifold. Okay, so it's sort of an explanation of like, because I've always wondered, like, why is it that I take any fiber network at all and I dilationally strain it, and all of a sudden it strain stiffens at a critical strain, or I can shear strain it and then it will at a critical strain become rigid. It's because the manifold of critical points is, for second order rigidity, is codimension unity. Like that's why, right? I mean, you could design a trajectory, a non-generic trajectory that wouldn't intersect the critical manifold. And maybe you'd want to do that, right? Maybe if you were already on the solid side, let's say you were the fruit fly amniocerosa, and you wanted to be rigid forever and ever, right? But you needed to move through phase space. You could say, actually, I need to avoid the critical manifold. I'm already on the solid phase. I need to avoid the critical manifold. So I'm going to try to do that. And actually, it turns out that should I say this? I'll say it. The critical manifold actually has a beautiful sort of geometry and, you know, differential geometry. So like you can compute the second fundamental form and you can compute the normal. And actually they are all governed by sigma. You can write them all in terms of this one state of self-stress, which I don't understand fully because I'm not a mathematician. But that means that because we understand the full geometry of this manifold, it should be possible to design trajectories that don't intersect the manifold too, because it's smooth off the manifold. Okay, so maybe I should stop there. That got a little technical. I'm sorry, but that's all I have to say, and I can take some questions. Okay. Yes. Yes. It is. That's precisely what it is. There are, well, okay. The cool thing is, and maybe I'll say neither. I don't know. Both. Let me show you this picture because this picture has one. And okay, since there's a whole family of these, right, that is related by conformal mapping, as you say, which one did I pick to show you? Okay, I think the one I picked to show you, though actually now that I'm thinking about it, I'm not sure because I stole this from Tyler yesterday. There is a particular isogonal mode that exhibits the least non-affine deformation. And that happens to be the mode where you can parameterize basically the, you know, because there's a whole family of basically sigmas that have this feature. And there's like basically one that has the least non-affine motion. It also tends to be the one, and I don't fully understand this, where the areas are like most the same. Okay, but anyway, there's one state, and then everything else is basically just a perturbation away from that state. And there's kind of like one unique state that has the most affine deformation, and it's the nicest looking one. So maybe that's the one you should build if you were trying to build one. But yeah, there's a whole family, and for us, it's not a problem because we know how to basically parameterize the subspace in terms of the affine and the non-affine motion, and so we can move around in there how we want. Yeah. Yeah, Sheila.
Like, you look at an image of an epithelial tissue, is it clear that that network is energy optimized, or there could be other sort of objective functions?
Yeah, I mean, it's a really interesting question. I think what I would be interested in doing, because this only applies to things that are poised right at the critical point, but we think we have some examples of that from like, you know, this work where I showed you Karen Kasia's papers where we like went across the critical line in the embryo, right? So I would be kind of curious if you had some way of figuring out the system was poised at the critical point. If you looked at the architecture, then you might be able to go and look and say, is it optimizing other objective functions by looking at the structure? Because in the paper, which will hopefully be on the archive in the next couple of days, we also go through and like say, okay, what are some specific structural measurements that you could make to tell that you were in one of these classes of things? And so, yeah, presumably you might be able to, you know, use one of those to sort of try to figure out what the tissue is trying to do, if it's trying to optimize something other than being near the critical point, but it's doing that while doing something else. But I don't know. I mean, we just talked about how vertex models are kind of insane models for tissues anyway, so I wouldn't want to, I mean, one of the things that I sort of put in the open problem for students is that I have not talked about finite fluctuations at all. And there's a lot of interesting things that happen in second order rigid systems in the presence of finite fluctuations, and real tissues are in the presence of finite fluctuations. And so actually one very interesting question is, I don't know how much of this survives in systems. You know what I mean? Like, I don't know how much of the functionality survives at finite fluctuations, for example, because this is also brand new. So like, I can tell you that Ryan Hayward's things, which are centimeters, are fine because there's no thermal fluctuations in that system. But if I wanted to self-assemble one of these things, and then I wanted to know about its like, you know, finite temperature properties, that's something for future work and might be relevant for the biological systems and might make them look quite different. Yes?
Like they took into account the point perimeter length, like whatever, what if you looked at the angle?
Oh. That's really interesting. So it's a really good question. The short answer is that secretly, area terms in these models are kind of like bending terms for the following reason. So if you want to try to compute the area based on bond vectors, so you said, I said, oh, I want everything to be based on bond vectors for something like this. Then one of the easiest ways to compute the area is called the shoelace formula, and it's basically a series of cross products around the polygon, gives you the area of the polygon. And of course, once you have an equation that has a bunch of cross products between bonds, it's very similar structurally to a bending term in a model. And so the first thing I would say is actually that's why the behavior of the spring edge model I introduced actually is functionally extremely similar to spring network models with a bending term for fibers. They're almost identical in their mechanics. And so I guess one comment is like, it kind of is already in there a little bit. But the question is maybe an extension of what you asked is, what if I got rid of the L's entirely? Like I had no constraints on the lengths and I only had constraints on bonds. And I haven't thought about that. It's a really interesting question. I don't know if it would be stable, what would happen? Yeah. Yeah. Yeah, would be penalized in a system like that. That's very true. Yeah. Yes.
I mean, it sounds like a technical question, but I mean, how exactly do you optimize? Just move vertices around? And do you use conjugated gradients on the objective function?
Actually, what we do is we actually use that transformation to self-stress space I showed you. We do all of our optimization in self-stress space. So we change the objective function, which was a function of the L's, into a function of the sigmas because it's a linear mapping because of this geometry. So it's super nice because, or uphill, but yeah, we just do either gradient descent or fire or something. And what I'll say is, yeah, this is fixed incidence matrix. But it's kind of interesting because then you can, so the cool thing, right, is you take one fixed incidence matrix, these are all the same incidence matrix, obviously, and you get this whole zoo of cool stuff. And the question is, then you can think about an ensemble of incidence matrices and how they behave, right? And, and everything I've told you sort of survives looking at an ensemble of incidence matrices. But the only set of incidence matrices we've tried because it's just easiest to generate to make sure that we're always under coordinated is those they're random regular graphs generated from a Voronoi tessellation. So an interesting open question is how like a Mikado network or a diluted triangular network, how much of this survives in those other network topologies, which we want to do, but Tyler hasn't done yet. But probably a referee will probably ask us to do. So he's getting started on it. Yeah. Okay.
Thank you.
Yeah.